All right, so let's kind of go through this, and like, if, I don't want you to flip out and go, well, because some of these I had no idea what to do, okay? Don't flip out, okay? Don't flip out until I tell you to flip out, all right? And right now, none of you should be flipping out. Maybe no.
I like barely started.
Okay, there's a shot. Okay, so, let me give you some hints, Sean. Pay attention to the fact, like, for example, on, number 1, with those Roman numerals, so let's just start with that. In which situation do you have to use Roman numerals? All the time or just some of the time?
Some of the time.
Why? What determines
And they
when that time is?
different oxidation states.
Yes, and those are primarily gonna be in the middle, the ones that are in the middle of the periodic table. Typically lead, copper, manganese, iron, those are gonna be the big hitters. But just because it's in the D block doesn't mean that it's gonna have more than one oxidation state, okay? So silver, for example, can only be 1+, even though that's in the middle. So if you're not sure, this is why I've given you that sheet that says, hey, here's some helpful information. That says, so if you can find an element that has more than one oxidation state, that's when you use Roman numerals. So that's why, like on lead 2 and iron 3, that's why I had to put those Roman numerals there, because if Kevin comes to me and says, hey, Mr. Burkett, I need iron phosphate for a lab. Well, here's the problem. I go to the chemical storeroom, and there's gonna be iron 2 phosphate, and there's gonna be iron 3 phosphate, and they have different properties. So that's why you'd have to have those Roman numerals. But if you come to me and says, hey, I need magnesium phosphate, you don't need Roman numerals, because magnesium can only have an oxidation state of 2+. So you only use Roman numerals if there is going to be more than one possible oxidation state. On number 2, 2 of those should have Roman numerals. Gap, Sean, only 2, okay, should have Roman numerals. What? That I'm not telling you. No, I don't. No, I don't.
Are they in the middle? On the edge?
But you're racing right.
I'll tell you this, they're side by side, they're sequential. The ones that have to have Roman numerals are sequential.
I got iron 3 phosphate, but phosphate. Yeah, you're right.
They'll give it.
So we both second too?
Yeah.
I can do this. The math?
Vaughn, hush, hush. On number 3, because if the first number is wrong, the second, everything is going to be wrong. So on this, you're finding the percent composition based upon atomic mass. So you have to go through, find the total atomic mass of the compound, and then divide that by that individual molar mass. So because if the first one's right, probably the rest of them are going to be right. So that percentage on number 3 for the sodium should be between 25 and 30%. Okay? And the one for manganese on number 3, that percentage should be around 15. Okay? Gap, Sean, are you happy with that?
Yeah.
Okay, because that's, I wake up every morning and go, what can I do to make Gap Sean happy? On number 4, that's just a simple mole conversion, okay? Now, I don't care where you've come from, Chem 1, Chem 2, May South here. You have to understand, like on mole conversions and things like this, if I don't see the work, I'm not buying it, okay? So it's like on number 4, if all I see is a number that magically appears, don't even bother, okay? Don't even bother. I'm more concerned about the process than I am about the product, okay? So here's how I'd want something like number 4 done. You have 0.238 moles of strontium hydroxide. Now, obviously, what's the first thing that you have to do this problem? What do you have to have right?
Figure out what strontium hydroxide is.
Yeah, you gotta have the formula for strontium hydroxide. If the formula for strontium hydroxide is wrong, everything else is going to be wrong. So is the formula for strontium hydroxide SROH?
No.
No.
No, it's not. Why?
It's SRH2. Strontium has a charge. plus.
Strontium has a charge of 2+, it's in the second column, okay? Why didn't I call it strontium 2 hydroxide?
Because there's only 2+ for strontium.
Yeah, because I can't have more than one possible oxidation state. So that needs to be SROH2. So then come down here, no, I know 1 mole of strontium hydroxide, and then you're gonna go to the periodic table. So that grams should be around 30. Okay? So that first mole conversion, that answer should be around 30. On the cobalt chloride, notice chlorite, that answer should be between 0 and 0.2. Closer to 0.2. Cool with that. Okay. Now, let's talk about some of these reactions, like that potassium chlorate one. So one of the things that, and this has been the universal struggle of chemistry, is particularly dealing with gases. So let's do a simple one you probably guarantee you've done way back in your simple days in Chem 1. So I'm going to take some hydrochloric acid and to that I'm going to add some magnesium. Okay? So got a very nice reaction taking place. Hey, we're generating a gas. So I'm going to collect that gas in a test tube. So there's certain gases that you can produce. Now, here's the problem with typically producing gases, is that, and this is a cool thing, hydrogen, carbon dioxide, oxygen, nitrogen, most gases don't interact with light. Okay, photons come through them, they don't interact with them, and that's cool, okay, because our atmosphere is mostly nitrogen and oxygen. If nitrogen and oxygen, if either one of those like absorbed light, for example, we couldn't see the sun. We would be in eternal darkness. If nitrogen and oxygen absorbed light, our atmosphere, our life would be completely different because that light couldn't pass through. So I'm generating a gas that clearly, I can see that, I can see the bubbles, but once that bubbles go up, it doesn't interact with light. So, hold that, light that. So we're going to do a little flame test. Okay, so we're going to get that going. Okay, now if I feel this test tube with hydrochloric acid, that's really, really hot. So if I take this and put this up in there, make pop. So what gas was being generated?
Hydrogen.
Hydrogen. Okay, so any time you do a flame test and you get that popping sound, there's only one gas that makes that sound, and that's hydrogen. So we can't see what it is, okay, because it's clear, it looks like any other gas, but we can do a flame test and go, oh, that produced hydrogen gas. So, and this is going to play out when we get to the next part. So I took elemental magnesium and dropped that into hydrochloric acid. Is hydrochloric acid a strong acid or a weak acid?
Strong.
Strong acid. This is like one of the poster children for strong acid, hydrochloric acid. And we'll talk more about this later. But the short version of the strong acid means that it completely ionizes. So on those lecture notes that I gave you, so that I handed out, one side is a summary of solubility rules, okay? And the other side of that is a list of strong acids and their bases, and we'll talk more about this whole thing. But here's the general rule for now. The stronger the acid is, the less attraction it has for the anion. So basically what that means is if you have molecular hydrochloric acid and you put it in water, it disassociates. It has a stronger attraction with the water than it does with the chlorine, and that's why it completely dissolves. So, the sooner you begin to shift your focus beyond just a Chem 1, oh, here I'm going to balance the equation, to actually understand the structure of what's taking place, the better off you're going to be. So you've got elemental magnesium, and in reality, that's existing as hydronium ions and chloride ions, okay? We write it as HCl, but in its molecular form, on an atomic level, you have a hydronium ion, otherwise known as a proton, and you have chloride ions. Now, these chloride ions are very stable, okay? Chlorine, Cl, has 7 valence electrons. It's gained another electron, it's happy, it's Cl1 minus. So the chlorine at this point could care less about reacting with the magnesium. So this is what we call a redox reaction, okay? Redox reactions, if you don't remember, here's the short version. Leo says Ger, so it's a Leo the lion. If you lose electrons, that's oxidation. If you gain electrons, that's reduction. So basically what happens is that the hydronium ion comes up to the magnesium, and that magnesium, if you do like the electron dot, it has 2 outside valence electrons because it's in the second column. So the hydronium ion comes up to the magnesium and goes, sup, mind if I dance with your electrons? Now, the electrons, I mean, you need to view this with magnesium as electrons. So magnesium, like about all heavy elements, was formed in the collapse and death of a neutron star. Got kicked out into the universe, reassembled onto this third rock. Magnesium then was purified and forced into this little ribbon. It's been sitting in the drawer back there in the chemical storage. So this magnesium and its electrons, they're tight. They've been through a lot, okay? Survived the death of a neutron star, got kicked out of the cold universe, got reassembled into this rock, got mined, processed, put into a plastic bag, sat in the storeroom at Mays High School, taken out, dropped in hydrochloric acid. So they've been through a lot. So basically what happens is that this hydronium comes up with these electrons and goes, hey, want to hang out? The electrons go, we're out of here. And the magnesium nucleus is probably going, man, we've been through a lot. You just jumped ship for some little proton? God. Huh. Okay, so the proton, the magnesium is going to feel a little left out. It's like, no, we've been through a lot. Some little proton comes along and, I'm out. Okay, well, fine, whatever. So it's a tug of war. So basically, those 2 valence electrons on the outside have a stronger attraction for that single proton than they do with that nucleus that they've been through everything together, okay? But when hydrogen takes in that electron, you're going to form hydrogen gas. So out of this, we write this as H2. So quick refresher on your diatomics. It's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, ion. So it's kind of like a 7. You start with hydrogen, and so if you have the elemental form of those as a gas,
I was looking at my periodic table.
there you go. You're welcome. So when those come together, they pair up, okay? And they pair up because, and for those of you that haven't had me, one of the things I preach, especially in chemistry, is more important in chemistry than it is in physics, is that Mother Nature is a lazy prima donna. So hydrogen comes together and they form a bond because that's the simplest form for hydrogen to exist in. So out of this you get hydrogen, and then we write this technically as magnesium chloride. So in a Chem 1 version of this equation, that's H2 plus MgCl2 and you balance it, and you put a 2 there, and that's simple. So there's the Chem 1 version of this. In chemistry, we don't care about the fluff, we only worry about what's really gonna change. So if you were to ask to write the net ionic for this particular equation, so magnesium chloride, because this is obviously in an aqueous environment, you need to decide is magnesium chloride soluble or insoluble. Well, all chlorides are soluble basically except for silver or lead. So basically what happens is that magnesium, once it loses those electrons, it dissolves and it turns into magnesium ion. So there's a huge difference between elemental magnesium, which is a strip of silver metal, and a magnesium ion, which is going to float around in water. Okay? They are not the same. Okay? It's tough, and I cannot emphasize this enough. Elemental magnesium and magnesium ions are two completely different things. Do they have the same number of protons and neutrons? Absolutely. But once you lose those two outer shell chihuahuas, it cannot exist as a strip of magnesium. It has to go into the solution. So basically, what happens from a story perspective is that if you look at this and you go, okay, here's this solid piece of magnesium, and once the hydrogen comes along and it takes away the chihuahuas, the other magnesiums kick it out and go, man, you traitor, you gave away your electrons. You can no longer stay in the club. You've got to go out into the solution side of this thing, traitor. But then all of them do it, so they all get kicked out, so that no one really gets to act too sanctimonious about the whole thing. Now, so on this, you have magnesium, and you have hydroniums, and you have chloride, and that's going to turn into H2, and then you have Mg2 plus Cl minus. So what's the only spectator ion in that reaction?
Chlorine.
Chlorine. So if you were to ask to write the net ionic equation for this, your chlorides would drop out because they stay the same. Because chloride is sitting there going, dude, I've got my 8 goats. I don't care what the rest of you do. I'm just going to chill out and watch what happens. I'm just along for the ride at this point. I could care less. So the magnesium turns into Mg2+. Now, every equation, especially net ionics, have to balance on 2 things. It has to balance on number of particles, and it has to balance on charge. 2 of the great conservation laws that exist in all of science. Law of conservation of mass, law of conservation of charge. So to balance this, I got to put a 2 here, because that's going to do 2 things. That's going to give me 2 positive charges on the reactant side, which is going to balance out the Mg2+ on the right side, so my total number of positive charges balance. And I balance out 2 hydrogens and 2 hydrogens. So the net ionic equation between magnesium and hydrochloric acid is going to be this, okay? And that's all we care about. Is the chlorine there? Yes. Does it matter? No, because it's not involved in the reaction. We care less about it, okay? It's just there. So that's kind of the difference between a net ionic and a regular equation. And again, I emphasize this. Your net ionic has to balance on charge and number of particles. Now, so stop the auto camera for a second. So let's go to the back